Welcome back, chemists. Today we're going to talk about the properties of light. So light is part of the electromagnetic spectrum. The electromagnetic spectrum is a range containing all the possible frequencies and wavelengths of electromagnetic radiation, and light is part of that electromagnetic radiation. But what we can see is just a teeny tiny part of the spectrum. In order of increasing wavelength, we have gamma rays, X-rays, UV, visible light, infrared radiation, microwaves, and radio waves. So over here on the right side of this, those are the longest wavelengths, and over here on the left, those are the shortest wavelengths. And we'll talk about definition in a second. Now, frequency is the exact opposite. So frequency, you will have the highest frequency to the left and the shortest or lowest frequency to the right. So that's really important. We need to know that if frequency goes up, then wavelength goes down, or the opposite is also true. If wavelength goes up, frequency goes down. So make note of those two processes. They are what we call inversely proportional, meaning one goes up, the other goes down. All right, parts of a wave. So the very top of a wave is called a crest. The very bottom of a wave is called a trough. Now, what's characteristic of waves is that they move up and down across a middle line. This is your middle line. Now, the distance from the middle line to a crest or a trough is called the amplitude. So that's just a distance here. And the distance between two crests or two troughs is called a wavelength. The symbol for wavelength is this called lambda. You don't need to know much about it besides that it is named lambda. All right, so talking about our electromagnetic spectrum, we had radio waves had the longest wavelength. So it was the longest distance between two crests, whereas gamma rays had the shortest. So a gamma ray would look kind of like this. Very, very short wavelengths. Right, there are two different ways we can describe light. We can describe light as a wave or as a particle. So light exhibits wave-like behavior as it travels through space, meaning that it oscillates back and forth across a midline, like so. Wavelength is the distance between two peaks, and we can measure it in meters, centimeters, or nanometers. Frequency is the number of waves that pass a given point in a specific time, and we measure that in hertz. And what hertz means is waves per second. Now, if we go back to that idea of our radio waves versus our gamma rays, if we say that this is about 1 second interval, you can see that we have 1, 2, 3, 4 waves per second, and we only have 1 wave per second over here. Now, those aren't exact numbers, but now we can see how wavelength is longer, frequency goes down. Wavelength is shorter, frequency goes up. All right, and then the speed of light is 3 times 10 to the 8th meters per second. Now that is pretty fast. So that's a 3 with 8 zeros behind it, which is 300 million meters per second. Okay, light can also be described as a particle. And Planck discovers the particle nature of light. A photon, discovered by Einstein, is a particle of light. So if you're talking about a particle of light, you call it a photon. It has roughly 0 mass and a quantum of energy. Now, what is quantum? Quantum is the minimum quantity of energy that can be lost or gained by an atom. So it's just like a little packet of energy. Therefore, light has dual wave particle properties. You also might hear this called wave duality. And all that means is that light behaves like a wave and a particle. All right, last thing about light is the photoelectric effect. Now, Einstein studied this. So he figured out that if you shine enough and intense enough light on a piece of metal, it shoots off electrons in all directions. So he just would shine light and maybe no electrons would come off. Then you shine light some more and then, oh my goodness, electrons would start popping off all over the place. And so he called that the photoelectric effect. Now that can produce color whenever you're releasing electrons from certain types of metals. Now, the wave theory of light could not explain that effect, so that's why we had to move on to the particle theory, which led us to dual wave theory. Okay, so all we need to know about this is that you shine light on a metal, electrons can pop off. All right, that's it for today, guys. Thanks for watching.